Today we will start with a plenary session PPS4 with Dr. Professor Felipe Lopes from Federal University of Paraíba in Brazil, who will address a very timely and interesting topic about protection of transmission lines. Professor Felipe, welcome, and the floor is yours.
Thank you, Professor José Carlos, for the nice introduction. Let me see if I can share my screen here. Do you see my screen?
Yes, you can see the screen.
Great. So, thank you again for the nice introduction. I'd like to thank all the attendees for being here to listen a little bit about what we have done in the past years. My presentation is entitled Using Traveling Waves to Protection Transmission Lines that Interconnect Inverter-Based Resource. And I cannot forget to thank Professor Kleber for the invitation to share these results, which have been probably the most relevant results that I have had in the past 5 to 6 years within this research area with regards to the integration of inverter-based resource. Analyzing the profile of the attendees here in the WCNPS event, I have realized that people have different backgrounds, theoretical backgrounds, in such a way that I will start my presentation with a very brief introduction on the problem related to the massive integration of inverter-based resource and the main features that have challenged protection solutions. Then I will explain something about traveling waves, explaining the main concepts and the benefits of using traveling wave-based protection in IBR interconnecting lines. And finally, I will share with you all some lessons learned from research that have been conducted for years in my research group. And then I will present the final remarks. Just to make sure that we have the same overview about the problem, I took some reports from the International Energy Agency to demonstrate that the massive integration is a reality. Integration of IBRs is a reality, and we have no other choice to solve these problems rather than facing these challenges and trying to find alternative solutions that can guarantee the proper protection of interconnection systems. For instance, in this report here, we see that in 2024, variable energies, which include those that fluctuate during the generation, like wind and photovoltaic power plants, they are exceeding the amount of hydropower energy here, which is almost 70% of increasing in relation to 2022. It demonstrates that wind and photovoltaic power plants are indeed increasing, and we have to look at this problem. There is another report that I found to be interesting for this presentation today, which was that this is a report which shows the phase of integration of IBRs in several countries. And they divided these phases of integration into 6 phases. And for instance, Brazil is now in phase 2, which is basically the context of having a lot of generations interfaced by inverters, which still have minor to moderate impact on the system, resulting in faster and more frequent ramping of generators, for instance. But we are expecting to reach phase 4 until 2030, when, and in this case, we will expect to see this type of generation meeting almost all demands at some times during certain periods. And in this case, the importance of these generations will increase in terms of stability. And so, as I mentioned earlier, there is no choice rather than facing these challenges. And in this context, we know that protection schemes have been severely affected. This is why we are concerned about studying alternative solutions to protect the systems that interconnect these IBRs, because historically, we have heard a lot from utilities that several problems have taken place in real systems, especially regarding the reliability and security of protection functions, because these types of generations they change the fault response. And at least what we have heard is that the conventional protection, some of them, they are not able to properly protect the systems under certain conditions of operations of these generations. Just to better understand this concept, even if we talk about grid following technologies or grid following technologies, it doesn't matter, because in both technologies, we will see inverters being used to interface these generations. And since inverters are used, the power electronic device, they do not allow, or at least they do not support very high currents flowing through them. And in this context, we have to apply current limiters. And as a result, the fault response and the levels of currents that are seen during faults, they are very, very reduced. And this is a first challenge for protection elements, because since the early stage, overcurrents have been the most suitable behavior, most suitable pattern that has been used and to implement protection functions. But there are other challenges here. If we consider grid following technologies, for instance, these generations, they synchronize with a given grid by means of phase locked loops, which estimate the magnitude and angle of voltage at the connection point in order to synchronize the generation with the grid. But when these voltages they present very critical sags, these PLLs can present instabilities, and as a result, the estimated frequency can present errors, leading the IBR to operate with off-nominal frequencies, leading also the currents that are synthesized in their output to present a typical behavior. And this is very challenging for conventional protections. Similarly, there are a lot of people saying that grid forming generations are tending to solve some of these problems, and this is true. I agree, but we cannot overcome the problem of reduced currents. At least we cannot solve this problem if you are not paying more to have inverters that support higher current levels. But here, these generations will form the grid, and the controllers are a little bit different because they are not current controllers, but rather voltage controllers. And something like they do not estimate the frequency, but they calculate the frequency for a given power, active power, and its output. And so here we may have some impacts on these outputs here, depending on how you implement such a frequency drop here. But the main problem in this case, although these generations will be able to form grids, the problem is still the presence of inverters which require the limitation of currents. So if we consider the current limiters and also the controllers, the action of the controllers, the fault response, we can say that the default response is no longer dictated by the generator physical aspects that we use it to see for synchronous generations, but rather the controllers and the current limiters will dictate how these generations will respond to fault scenarios. So, given the importance of this topic, we published last year a paper which is entitled Maturity Analysis of Protection Solutions for Power Systems Near Inverter-Based Resource. This is a very interesting work, in my opinion, because we collected the opinion from 4 different research groups around the world, considering the groups from Brazil, from Canada, which have been led by Professor Ali Huxia, and from China, which has been led by Professor Dong. And there, initially, we mapped the main problems that have been addressed in the literature, and we could list some of them here, like low fault contributions due to the presence of current limiters, the unusual response of negative sequence currents, for instance, because the controls, they suppress or they change the patterns of negative sequence currents depending on the used grid codes. There is an atypical angle behavior, of course, because the controllers, they act changing angles and magnitudes. The IBR control requirements, and in this case, I mean the grid codes, we have seen that using different grid codes, the fault response can change. Frequency excursions, which are problems much more related to grid following IBRs. As I mentioned, the PLL may present instabilities resulting in frequency excursions. Memorized polarization issues, for instance, because when these frequency excursions take place, for example, the pre-fault data which was memorized, the pre-fault data quickly becomes invalid. So there is a lot of papers reporting problems related to this type of solution. And we have also read some works reporting the high dependence on communication channels, and also the problem of transformer terminated lines, which is the topology of most existing IBR interconnecting systems. And if we consider the context of phasor-based solutions, which are treated here as conventional solutions, and when we consider also the traveling wave-based solutions, most of these problems, they are expected to affect phasor-based solutions, but only few are expected to affect traveling wave solutions, as you can see in these colors, in these different colors. The high dependence on communication channels is still a challenge for traveling wave-based solutions. And the terminations and the characteristic of the line terminations also do matter in this case. But these other problems here, they are not, they are not very important when we are considering traveling wave solutions. And the question is why? Why traveling wave solutions can be so robust to this problem that affect phasor-based methods? And this is what I will try to explain here in the next slides. Firstly, it is very important to understand what is a fault. Basically, we can have a system operating with an almost constant voltage. And at the fault point, it is expected to occur an abrupt volt variation, an abrupt voltage sag, in such a way that we can see like a step surge. But thinking about this step surge, thinking about this waveform here, which will appear at the fault point, we have to remember that fault quantities, electrical quantities during transmission line faults, they are the superposition of system loading and fault contributions. And what I mean is that we can apply the principle of superposition of pre-fault circuits and pure fault circuits in order to understand the fault. And in summary, when we analyze the fault from this perspective, what we are saying is that the system with fault can be represented by the sum of a pre-fault system with a pure fault system. The pre-fault system has information on the load flow through the system, but the pure fault system, it carries information on the fault only. And if we analyze the components present in pure fault circuit system, what we can see is that there is, of course, a fundamental component. There are low voltage, low frequency transients that can show up here as well. But the higher frequencies, they are related to the traveling waves that will be launched by the fault and that will propagate over the line. And this is the part of the spectrum that we are interested here in this presentation. And given this surge, this step surge, we can understand the propagation of traveling waves just by thinking about the surge that takes place in a given point of the line. It will change the profile of the currents flowing here through the inductance. It will be full of magnetic energy, and then it will pass the remaining energy to the capacitor and so on, in such a way that we can see the surge propagating over the line, having a travel time, a well-defined travel time. And since these parameters tend to be homogeneous for a given piece of cable, we expect to see a constant propagation velocity for a given type of line. A common analogy it can be drawn if we consider a mechanical wave that we can see when we swing a rope, for instance. But remembering that the mechanical wave is different from the traveling wave that we measure in transmission lines, because they are electromagnetic waves. I prepared here with some students an experiment in which we simulate a surge. The surge is my thing, and I just touch the rope there, and we can see the step propagating over the cable and reflecting. This is the principle that we can demonstrate in a very simple experiment like that, just to motivate you to understand what the travel waves, how the travel waves take place on a transmission line. And since they propagate and reflect from the system discontinuities, we can draw the Bewley diagram, which represents the travel wave propagation. And these waves, they propagate from the fault toward the line terminals, where they find discontinuities because there are other equipment connected at both terminals. Then they reflect back to the fault point. In the fault point, if we are talking about a permanent fault, they will reflect again, and part of these waves will be transmitted, passing through the fault toward the opposite terminal. But the main information here is that from these transients that these traveling waves will create, from these transients, we can extract information on the disturbance. And this is the main principle of traveling wave protection functions. If we consider that these transients are very fast, I mean, I am talking about very narrow transients in a very narrow time window, it's obvious that we will need high sampling rates. And what we have seen is that over the past years, various developments have been released in the market toward increasing such sampling rates and toward improving the traveling wave filters that are used. We can find equipment which use 5 megahertz, sampling rates of about 1 megahertz, and also some device with 10 megahertz more recently that has been released in the market, and among others that we know that exist that have been developed in China, for instance. But this characteristic shows that differently from the past, when a lot of researchers reported that travel wave-based solutions would be not feasible in the field. In today's technology, we have the opportunity to implement these protection functions by using these sampling rates, which have shown to be sufficient to analyze traveling waves on real systems. For instance, this is a real report, and we can see that there are transients here, and these are the transients that we are interested in. As you can see, they take place in a very narrow time window, and the question is now, how can these transients help protection schemes applied to IBR interconnected lines? So to understand that, let's see how the controllers and the system behave during a fault. If a fault takes place, there will exist a step surge on the voltage at the fault point. It will generate some transients and launch traveling waves over the system. But from the perspective of the controllers applied in the IBR, after the fault, a control reference step will be seen. There will exist a reaction time, and then the controllers start to act, trying to move the quantities to another point of operation. We know that there is a step response time within which most protection functions will try to take decisions, and I mean most conventional protection functions. And this is a problem because the controllers are still trying to convert to its final values. And this is why a lot of people have reported that waiting a little bit of time to take decisions using conventional protections would be beneficial, because after the settling time, the system tends to enter in the fault state. And by doing so, conventional protections could be reliably applied. But the problem is that there is a maximum fault clearance time that must be respected in such a way that limiting the time to take decisions here, it can make the application of conventional phasor-based protections very challenging in such a way that the second option would be only to accelerate the protection. And in this case, using these fault-induced transients, which usually show up during the reaction time of the IBRs, it comes to be very promising, especially because these transients are not affected by the source characteristics, and so the protection decisions could be made before the controllers start their actions. Just to demonstrate that this is a real record, and if we see the record in the scale of cycles, we can see the transients, but if we zoom that area, we can see in more detail some transients, but this zoom is not sufficient to see the traveling waves yet. But when we consider a scale in microsecond time scale, we can see that transients present characteristics like steps. And these steps are the traveling waves arriving at the measurement point. So when we say that we are looking for steps, we are saying that we are looking for traveling waves, because this is the conventional pattern of these transients that allow us to analyze traveling waves. And basically, we are interested here in detecting the travel time of these traveling waves, detecting polarities and also amplitudes. Just taking again a look at that video that I presented in some slides earlier. I will use it to explain what are the measured traveling waves, because when we apply the surge here, you see that at the traveling wave recorder, what we will measure is not the incident wavefront, but rather the superposition of the incident and the reflection. If I pass here the video again, you can see here that the rope will swing here, it increase, and then it decrease, because the measurement will be the superposition of the incident wave, and the reflection comes over this incident wave, and the measurement will be given by the superposition of them. Since the incident traveling wave depends only on the fault characteristics and on the line characteristics, which are much more concerned about the reflection, and this reflection will be determined by the line terminations. And this is where the problem, we can find the problem of using traveling waves in lines that interconnect IBR, because irrespectively of the type of generation here, we take the doubly fed induction generator and full converter generators as examples, but in any of these cases here, the connection after the inverters, there will be a transformer interfacing the generation with the grid. And this typical connection, basically, it forms a transformer terminated line, which, although it is not a problem for if we are analyzing fundamental components, for instance, if we are taking into account traveling wave-based solutions, it must be carefully analyzed. And just to explain why it can be a problem, let's consider here a line, transmission line, which interconnects an IBR. If we consider only the transformer here, for higher frequencies, it will behave as an open circuit, but for low frequencies, it will behave as a short-circuited path. And so if the fault launches traveling waves, and I am here talking about current traveling waves because most of existing protections based on traveling waves, they are based on current traveling waves. And in this case, the traveling waves will reach both line terminals, and reflections will appear. On the grid side, where usually there are other transmission lines emanating from the bus, it is expected that the wavefront will see the parallel of the parallel association of the sub-impedances of all of these lines. And this parallel association will be smaller than the sub-impedance of the line from where the travel wave is coming from, and such a way that the measurement will be the sum of the incident wave and the reflection, which will be positive, a positive reflection, and it will amplify the measurement here. But on the IBR side, due to the presence of that transformer, the transformer will change its behavior because it has a very strong inductive effect. And in this case, if we consider the superposition of these wavefronts, what we would expect for the systems was like something like that. But is that realistic? I am considering here only the transformers, and the answer to this question is no. It's not. This is not realistic, because when we consider higher frequencies, stray capacitances will show up or in between the transformer windings and in between phase and ground here. So this is not a realistic analysis, and we can prove it by considering a real measurement of traveling waves in an IBR interconnecting line. This is a real measurement of transients considering 1 megahertz sampling rate, and we can see that on the grid side, there is a step-shaped transient as expected. But unlike this shape here, we see on the IBR side a very fast tentative of forming a step change, but which quickly decays with an exponential envelope. So it shows us that there are stray capacitances over the transformer and the busbar capacitance, and they will affect the measurement because now when we consider these capacitances in parallel, at least from the perspective of transients of surge, they are in parallel with this transformer. So these capacitances will dictate the behavior of the measurements. And actually what we will see is something like that, with reflections. And at the end of the history, we will measure a step change on the grid side and a quick step here, which decays exponentially after some time. So the stray capacitances play an important role for traveling wave-based applications, and this is the topic that we have investigated a lot in the past years. Considering off-the-shelf device, the traveling wave filter that has been used is the differentiated multi-filter, which we call here DS filter. Basically, this filter responds to step change with triangular shaped outputs. And when the step change starts to be attenuated, forming a ramp change, the filter starts to respond as a parabola shaped output. So we expect to see almost shapes almost like triangles on the grid side, but since we are expecting this pattern here of transients, the output of the DS filter will tend to present a parabola, and then it will oscillate, and then it will converge. And so we started to analyze this problem, considering initially simulations, where we implemented in PSCAD this type of system, a typical topology of interconnection of IBRs, and we varied the capacitances over the transformer. And what we could see is that these results indeed show up. Here, for instance, for a fault, for an internal fault here on the monitored line, we can see if we take measurements from the local bus, which is the side, the IBR side, we can see these oscillations, but they do not appear when we take measurements from the remote bus. Here we can see a parabola or like a triangle, and here something that oscillates. And most importantly, we can see that when we vary the stray capacitances here, the amplitudes change more on the IBR side rather than on the remote bus where the grid is connected. And there is an important aspect that I have to point out here as well, that when a fault takes place behind the transformer here on the point F2, the stray capacitances in between the transformer windings, they are very small, in such a way that only very attenuated traveling waves are measured at both ends, because they are attenuated here. So we measure a very attenuated wavefront here on the local bus, and then a very attenuated traveling wave also on the remote bus. As a consequence, this principle has been used to implement some new protection functions based on traveling waves, as I will explain later on. So some remarks about existing traveling wave protection solutions. Usually, we know that coupling voltage transformers, they have full frequency response. So if required, most traveling wave solutions analyze only the first voltage traveling wave. But there are other solutions that try to overcome the need to analyze voltage traveling waves, just taking the information from the instantaneous values of voltages when current traveling waves are detected. Regarding current transformers, for this type of application, they have shown to present an acceptable bandwidth, and most existing traveling wave functions, they are based on current traveling waves. The analysis of traveling waves reflected from the faults possible. We have seen single-ended traveling wave fault location, for instance, which detects the reflection from the fault. But this task is still challenging because it requires the reflections to be distinguished from other traveling waves. So it has somewhat limited the use of reflections in protection solutions, although we hope to see something in the future. And given this context, various types of functions and schemes have been proposed. For example, we can find the directional elements which have been used to implement also pilot protections like the POTT scheme. We have seen overcurrent elements, differential elements, fault location, distance protection, but distance protection requires the detection of reflected waves, so they are not uh, yet in off-the-shelf device. But these other schemes here we can find or we can implement using existing technologies already. So just to explain briefly here these functions, travel wave fault location is not exactly a protection function, but it has been used to as an auxiliary function for protection schemes. And the double-ended methodology is the one that has been mostly used, most frequently used in real applications. And basically, it detects the first wavefront at both line ends and calculate the fault location, the fault distance using this formula here. The overcurrent traveling wave element, it compares amplitudes of currents with thresholds, which are defined from expected fractions of waves that pass through terminal stray capacitances. Such an element was presented in this paper. And the idea is if there is a line fault, it is expected to measure a strong wavefront here. But if there is a fault behind the transformer, only weak wavefronts will be measured because they will pass through the stray capacitance over the transformer, and it will attenuate these wavefronts in such a way that we can distinguish case of line faults and faults behind the transformer. There is a very interesting traveling wave-based directional element, which I considered here. Is not exactly the one that has been implemented in off-the-shelf device, but I do believe that this function is very promising because it compares the relative polarity of current traveling waves with the voltage sample, some samples before the detection of the current traveling wave. By doing so, they overcome the need of measuring transients by means of CVTs, and they take the reliable measurements from the CTs, and by doing so, just comparing the polarities of these wavefronts, they can distinguish forward from reverse faults. Forward faults are those that the voltage sample and the current traveling wave, they present the same polarity, and reverse faults, in the reverse faults, they represent opposite polarities. And the solution you can find in this paper here. The traveling wave-based differential scheme, and it compares the polarities and amplitudes of traveling waves at both line ends. You can find further details on this paper. And basically, for internal faults, we can see that the first traveling waves that will reach the transmission line, they will be separated by a time period which is shorter than the line travel time. But for external faults, they will be separated exactly by the line travel time. And given that for internal faults, the polarities will be the same, and for external fault, the polarity of these wavefronts will be opposite between each other, one can calculate differential and restraining quantities in order to apply these operating conditions, like the classical ones, which compare differential quantities with slope multiplying a restraining current, They can compare the differential current with a pickup value. They can verify whether the measurements, the travel waves measured at both line terminals exceed a pickup value, and also a security layer here, which considers the fault location function just to make sure that the fault is within the lines. So to demonstrate the effects of the stray capacitances on these functions, we simulated in PSCAD 1024 fault scenarios. And I would like to thank Moisés Davi for the support in doing these simulations. This is published and you can find in our publications, but basically we simulated that three faults. The point F1 is related to an internal fault, F2 and F3 are external faults on the IBR side and on the grid side. Different fault features we're considering, and we varied the stray capacitances considering different IBRs like doubly fed induction generator and full converter wind power plants. Just to see when we change the stray capacitances for fault F2, for instance, a little bit change. There is a minor variation here in the wavefronts, the filtered signals. But when we consider the variation of the busbar capacitance here, we can see for our internal fault, the measurements, they change a lot their amplitudes here, which is cause of concern, at least for applications that consider measurements on the IBR side. Varying the capacitance in between the transformer windings, we can see that it matters more for external faults than for internal faults here. And if we consider the variation of the stray capacitance here on the low voltage side of the transformer, again, we can see some influence and also some reduction of the amplitude here when we change the value of these capacitances. These effects from the point of view of fault location, we can see that when these capacitances, they increase, very accurate response can be found, but when these capacitances decrease, we start to see additional errors, and it shows that fault location can present higher errors for cases in which stray capacitances are small in the system. Just to demonstrate here the directional and of the current elements, here we are comparing the current traveling wave with the voltage sample. For internal fault here, we can see that the elements operated properly, but varying the stray capacitance, we may, depending on the threshold that is chosen, we can have some difficulties in properly detecting this wave here. On the other hand, on the grid side, the waves are very strong and no problems are verified. Actually, we didn't see problem here, but we could see a possible problem that could occur if I come to choose a higher threshold. For an external fault, as expected, travel waves are very attenuated, so they did not exceed the thresholds as expected. And here, an internal fault, actually an external fault on the grid side, when we see here different amplitudes, very different amplitudes when we vary the stray capacitances. On the IBR side, in this case, it properly detected the case, but it shows that the stray capacitance indeed play an important role for these functions. And here on the grid side, is okay. And just to make sure that you will believe in me, this is a real case where we can see that. So we can see the wavefront on the IBR side, the oscillation that I mentioned earlier to you. So this is real. The stray capacitance effect is real, but we can see that the wavefronts can be properly detected in the real system. So it shows that travel wave protection functions are indeed promising. And now, just to go to the ending part of my presentation, this is a sensitivity analysis that we carried out just to see what to expect from these functions by varying these stray capacitances. And for regarding the directional element, when we consider external faults behind the transformer on the IBR side, we can see that there is a behavior which is reliable because the elements properly see the direction of the short circuit on both sides. But for internal faults and for faults on the beyond the remote terminal where the grid is connected, we can see that there is a trend of reducing the amplitudes of the protection element torque, which shows that for small stray capacitances, we may have some problems here. Considering the overcurrent element, it is possible to conclude that for measurements on the remote side, on the grid side, they are very well behaved. But for measurements taken on the IBR side, the presence of stray capacitances, it will dictate the sensitivity of this function. So only for higher stray capacitances will see the quantities exceeding the thresholds and guaranteeing their operation. For the differential element, the same. We can see that the fault location is not severely affected. We can see that some conditions here for external faults are properly respected, and the amplitudes of the travel waves guarantee the proper operation. But one of the conditions can present some instabilities here, like in faults F1 here and F3 here, because they cross between each other, demonstrating that the differential current can change its behavior in relation to the restraining current, depending on the values of the stray capacitances on the IBR side. And this is why some manufacturers are recommending to block these functions depending on the stray capacitances that are measured on the IBR side. The final result is basically an experience that we had testing real device, and it motivated us to propose a recommendation for modeling this type of systems when you are interested in testing real traveling wave protections. For instance, by modeling a typical topology like that one without the busbar capacitance and with the busbar capacitance, the traveling wave protection, differential protection, for instance, it showed it did not operate when we did not model the busbar capacitance. But we know that this busbar capacitance, it exists. We only do not model it when we are considering conventional phasor protections, for instance. And by modeling the busbar capacitance, we could see in this paper that the traveling wave protection operated as expected, unlike the other elements which are based on other quantities rather than traveling waves that present the same behavior without and with busbar capacitance. It shows that stray capacitance must be modeled if you are interested in testing real traveling wave protection device in this type of system that interconnect IBRs. We could find this margin of sensitivity here. And this is why we usually say that the previous study on the stray capacitance are important to verify the practical sensitivity. Otherwise, if you have communications, you can monitor the grid side only and just release stripping commands to the IBR side if necessary. And my final slide is this one. In the same paper that I have already showed you, we performed a maturity analysis on these functions, and transient-based protections, they appeared as mature technologies because they have already a lot of papers investigating these functions. They have already been tested using real data. They are already feasible in today's technology, and they are very easy to generalize to different systems. So they appeared as a mature technology. despite all these challenges that are still to be solved. So, as my final remarks, I would like to say that the increase in sampling rates, it has led traveling wave applications to gain popularity. And in today's technology, these functions are undoubtedly a reality. And we do believe that they will gain space in the market in the next years. The travel waves can be analyzed earlier the, than the IBR control actions, and it makes them immune to the IBR controllers, for instance. They are in nature pure fault circuit quantities, and so they are immune to source features, which is very good if we consider the the wide variety of techniques that can be used to implement converters in modern power grids. Frequently, IBR interconnecting lines are terminated by transformers, as I mentioned during my presentation, and it can attenuate current traveling waves. But despite that, we could see a good operation in most of the analyzed cases. So the busbar and transformer straight capacitances will dictate the sensitivity of these functions. We could see that fault location, even using current travel waves, is not very, is only slightly affected because it detects only the line travel, the wave travel time. But we do believe that using voltages also for fault location functions would be beneficial. And I think that in next coming years, the manufacturers will release fault location functions that can use currents for voltages, not only one or another. We could see also that overcurrent, directional, and differential protections can lose sensitivity for small capacitances, but the real world case that we have analyzed so far, they have shown that these functions are indeed promising solutions. And it shows that the straight capacitances in practical situations tend to be sufficient to guarantee the sensitivity of these technologies. But I have to say that previous study on the straight capacitances is recommended to have an idea about the sensitivity of these traveling wave protections. And finally, the traveling wave protections are classified as a mature technology. This is why I do believe that further developments will be presented in the next years. Most of the solutions still require communications to implement tripping schemes. And I believe that in the next coming years, probably the functions will evolve toward allowing non-unit protections in this type of systems and being even more independent from other auxiliary functions that are usually applied to guarantee the reliability and security of traveling wave protections. So this is my presentation. I would like to thank you very much for the invitation. It's an honor. Thank you. And the word is yours, Professor José Carlos.